Hi, NA Physics, it's Mr. Neff. I want to continue our talk of line spectra today. But before I start that, do you know what you get when you cross a kitten and a fish? I'll tell you about that at the end of the video. Here's an energy level diagram for just some fictitious atom. You can see we've got transitions A, B, C, D, E going on there. And so I'm asking you here to arrange these by wavelength, shortest to longest, frequency, lowest to highest, and energy, least to most energy of the photons that will be emitted whenever those happen. You know, all of these are emissions of photons because we're going down. I want you to pause the video here and try to get in order. Really and truly, pause this. This is a great skill to have. Okay, so I hope you took care of that. And if I move this over, you will see that the wavelengths are arranged so that the ones that have the shortest wavelength are the ones that have the highest energy. And so you see that the electron fell the farthest. Frequency, lowest to highest. Lowest frequency is going to be the one that has the lowest amount of energy. And so that's the shortest trip. C is real short, as you can see there. And then frequency and energy are directly proportional. You just multiply by Planck's constant to go from frequency to energy. And so there you have the same order for the energies. So now all of this is evidence of light's particle nature. Light is acting like a little bundle, a photon, with a quantum of energy that's coming in instead of a continuous wave. A wave doesn't really have, I mean, you could turn it on and it could have a beginning, but where do you say, right there, that's it, that's an amount of energy, and the electron's going to absorb just that much? Well, nowhere exactly. And so this is light acting like a particle. And we'll also say that the amount of energy brought in only depends on the frequency. It doesn't depend on the intensity. You would think the brighter the light would be, the more of this you would see. That's not the case. You only see more electrons happening, not higher and higher energies per electron. So check this out. Here are 4 behaviors that light shows from time to time. Some of these show that light acts like a wave, and sometimes it shows that it acts like a particle. I want you to classify each one as wave or particle. Stop the video, classify. Okay, very good. And I hope that you saw that most of these are wave. Light bending as it passes between mediums is a wave. Light shining through a hole and doing interference. Interference is a wave behavior. Polarizing light, that's a wave behavior. But atoms emitting and absorbing light of only one specific wavelength, that's particle, because there again, the light that's coming in is behaving like a little bundle of energy. Okay. Now, the energy an electron has is the sum total of its kinetic and electric potential energies. Electric potential energy compared to this free electron out here, and so it's going to be negative. And actually, all of these total energies are going to be negative because there's going to be a bigger negative contribution from the electric potential energy than the smaller contribution from the kinetic energy, and I can show you why that is. You remember that kinetic energy is 1/2 mv squared, of course, and you also remember that electric potential energy is the integral of Coulomb's law. And so here I have Coulomb's law, KQ, the charge on the nucleus is the atomic number Z times the elementary charge. The charge on the electron is the elementary charge, so there's Z elementary charge for the nucleus, and then another elementary charge for the electron, and then it would have had a square, but that gets integrated away. Now, I can say, because of electric force being equal to centripetal force, that the electric force is equal to 1/2 mv squared. And so I can play with that a little bit, and I can get myself to a point where I can substitute 1/2 of this for the 1/2 mv squared. So after you combine all of this, you're going to get a total energy of that for that energy level. Coulomb's constant, atomic number, elementary charge squared, divided by 2 times the radius. And that is That is going to be negative because there again, it is compared to that free electron out there. Now you can recall that the angular momentum of a thing going around in a circle is the r cross the linear momentum. Technically, these should have, it's a cross product, so these should all be vectors. Bohr made a weird assumption about the angular momentum, and he thought that it would be a quantized version or integer multiples of h bar. Remember that from the one video, that was h over 2 pi. It was a crazy assumption, but it turned out that it held up in practice. And so he did some substitutions this way, and I will not bore you with this part. In the end, he realized that the size of the radius is going to be calculated this way. And it is going to depend on the quantum number, the n, and then it is going to depend on the atomic number of the atom, the number of protons that you have in there, always times this constant. So if you combine all of this, combine the radius and the thing that I just came up with for the energy, then you can do this, and you can say that the energy level that something has is going to be negative 13.6 electron volts times this fraction. And you have to admit that looks a little simpler than those last two things. So this is another time where we like the cleaned up version more. Now that's a way to calculate those energies directly. And we can't disregard that, but you could figure those out with the radii, but you could also sort of cheat, and you could see what the element actually absorbs or emits. So we know that an energy of a photon is hc. Well, of course we know that it's hf, and f is going to be c over wavelength. So we can say that it's the energy hc over wavelength. Now that's nice because h and c are both constants, and so it's helpful in not in SI units exactly, but it's helpful to know that hc is 1240 electron volts times nanometer. So now what you could do is you could say, hey, here's hydrogen, and I can see what colors are either missing from the absorption spectrum of hydrogen, or what colors are in the radiation spectrum of hydrogen. And so it turns out that these are the colors right here. And so now I ask you, based on energy is hc over wavelength, where hc I just gave you, I ask you what energies correspond with those lines. I'd like you to stop the video here and try to calculate those. All right, so all you had to do was take the amount of nanometers that I gave you and divide hc by it. And if you did that, you get these energies, and I'm certain that everybody got those. Now, do those show up on the energy diagram? Yes and no. Notice something. I still need the equations from the last slides to calculate these 13.6, because that isn't going to show up visually. Remember, that is ultraviolet. Not that we can't detect that, but that is ultraviolet. And I still need the equation to calculate the 3.4. But now, do you see something? Do you see how the 1.89 shows up? The 1.89 is the amount of energy associated with this transition right here. And so it must have come from a place that was 1.89 electron volts higher. And guess what? It sure did, right? It did. And what about this one? Well, that must have come from a place that is 2.55 electron volts higher. And guess what? It sure did. It came from that place. And we could keep on going down like that. So there's, just like so many times this year, there's a forward way and a backward way to do everything. So now it starts to all come together, and you can see that if you're dropping into the n equals 1 state, you're going to get those really short wavelength, really high energy photons coming out. These are going to give you your UVs. Those did not appear in any of the pictures because good luck photographing that. If you drop into the n equals 2 energy state, you're going to get those visible lines. And they keep going up. You can drop into 3 and get infrared. You can drop into 4 and get longer wavelength, 5 and longer wavelength. And if that's something that you're interested in, those are all named after scientists. These energies over here, and the reason that I brought this slide up, these energies over here are the ionization energies. If that much energy came in or more, this is the only time where it could be or more. But if a photon that was 13.6 electron volts or more came in, then that would take that electron that was in that state and wham, ionize it, get it off of the atom. It's not as hard to get this one because it's already, part of the way off. And so that would only take 3.4 electron volts, and so on and so forth. Just a couple of examples before we go. Here we say, according to the Bohr model, what determines the shortest wavelength in a given series of wavelengths emitted by the atom? Pause this and come up with an answer. Well, a lot of these answers are pretty good. A is pretty good. So the final quantum number, well, that determines it. Sure, it does. It's what energy level you're dropping into. But it depends on how far. If you're dropping into this energy level, say, and you only came from there, well, that's going to be a small amount of energy, so a longer wavelength. If you drop from farther, it's shorter, and if you drop from farther yet, it's even shorter yet. So it depends on where you're coming from, too. And so B is also an okay answer. It depends on where you're coming from. The ratio, not so good. The sum, not so good. The answer that I picked is E. What matters is the difference between those two. You want to get the difference to be the biggest possible. Hey, take a look at this. An atom with these energy levels could not absorb or emit photons of which of these energies? Pause it and come up with an answer. Well, could you go 1? You bet you could. You could go 1 either way. Could you go 2? How about 2 like this? 2, 2. Could you go 3? From 5 to 2 is 3. What about 4? Sorry, don't see any 4s. Take a look at this one. What photon energies could you get from this atom? So it's the same one. We already saw that you could get 1, 2, and 3. Could you get anything else? Try to come up with what else you could get. Well, like we said, I got 1 there, so 1 electron volt will work. I got 2 electron volts. 3 and 3. It looks like I could also get 3 between 8 and 5. I could get 2 between 10 and 8. But what about farther? Could I go 8 to 3? Yeah, there's 5 electron volts right there. 5, 5. What about from 8 up to 2? Well, there'd be 6. What about 10 up to 3 and 10 up to 2? Well, you could see I could get 7 and I could get 8. And that's my extremes right there, right? When I go all the way from 10 all the way up or all the way down, that's going to give me that 8 as far as I can go. So 4, it turned out, was the only one you couldn't get. Okay, our last example here, and this one takes a little bit of time, and I'm going to ask you to pause it and really try to get some great answers here. We've got a diagram here, and it says A, electrons initially in n equals 3 undergo transitions and emit photons. Draw arrows to indicate all the possible transitions for those electrons. And then B, of those transitions, which one has the longest wavelength? What's the ionization energy? What effect will an 11 electron volt photon have on the electron in the ground state? And what effect will the 14 electron volt photon have? Pause it and come up with answers to all of those. Okay, and we're back. So you can have a transition down, or, and this is one you wouldn't think of necessarily, you could go down, down. And so all of those end up giving you those. So you could go straight down or all the way down or in 2 steps. That'll give you 3 different energies. Longest wavelength of those is going to be the one that has the smallest energy. So that's going to be the 3 to 2 right there. and that's going to be the difference in energy on the denominator, 551. Ionization energy is easy. It's just that 12 electron volts down there. 11 doesn't correspond to any of them, and 14 electron volts will remove it.